In this video, we're going to introduce a different coordinate system compared to the one we've been using. We were used to using the rectangular coordinate system or Cartesian coordinate system, which consists of points x and y. Now, the polar coordinate system instead consists of a fixed point called pole and a ray called the polar axis. So, a polar coordinate system consists of a fixed point O called the pole and a ray called the polar axis. And then every point P is defined by the ordered pair R theta, where R is the directed distance from the pole to the point P, and theta is the directed angle from the polar axis to the line OP. So instead of defining a point based on x and y coordinates, we're defining a point based on the distance away from the pole and the angle that that line through the pole and the point makes with the polar axis. So just a quick sketch of what this might look like. If this is my pole O, and here's my polar axis. Let's just say we have this point P up here. Well, R is going to be that distance between O and P. Theta is this angle that is formed between the polar axis and the line formed by OP. So if our R is positive, then P is R units from the pole in the direction of the angle theta. If R is negative, then P is R units from O in the direction theta plus pi. So for example, up here I have a positive R for my point P. If I instead had negative R, instead of going in the direction of where my angle theta is, I would move in the opposite direction, theta plus pi. So I would have my point P down over here at some point. When theta is positive, it's considered a counterclockwise angle, and when theta is negative, it's clockwise. So let's do an example plotting some points so we get used to what this looks like. Let's plot 3, 5 pi over 4, 4, negative 7 pi over 6, 2.5 and 4 pi, and negative 3, 4 pi over 3. So let me make my axes. And to make it a little bit easier, helping us find our R's, I'm going to make very lightly some circles with increasing radius. We only need to go up to R is 3, so I'll just go ahead and go one more just to show us where R is 4. So my circles that are getting bigger and bigger as I go out, we have radius 1, 2, 3, and 4 for those circles. That'll help us determine the proper distance. So our first point, 3 and 5 pi over 4. An angle of 5 pi over 4 is positive, so that means I'm going around counterclockwise. 5 pi over 4 is this angle down here that I'm marking in orange. Now, I need to be at a distance of 3 along that angle. So I have 1, 2, 3. Here's my point right there. That point in orange is the point 3, 5 pi over 4. For my next one, I have an angle of negative 7 pi over 6. So I'm going to be going clockwise. Going negative pi would get me all the way over to this left side, and another pi over 6. I'm talking about this angle right about here approximately. And then I have 4, and so I need to be a distance of 4 in that direction. Puts me on that circle of radius 4 out there at that particular point. So I have the point 4, negative 7 pi over 6 is that point right there. For the next one, I have an angle of 4 pi. Now 4 pi, we know we go around once to be 2 pi, go around again, that's another 2 pi, so that's 4 pi. 4 pi is an angle that's going directly out to the right. The distance of 2.5 means that my point will be right here in between the 2 and the 3, right at 2.5. So this point here is 2.5 and 4 pi. And the last one, an angle of 4 pi over 3, and it's positive. Well, 4 pi over 3 would be approximately this angle down here. But I then have an r of negative 3. So instead of going along 3 in the direction of my angle, I have to go backwards 3 spots. So my angle is over here, and I'm going back 1, 2, 3. And that gives me my point of negative 3, 4 pi over 3. Now you might notice that there's more than one way to write all of these points. In fact, there's infinitely many ways to write our points in polar coordinates. For example, the point that I just did, I could have used the angle pi over 3, and then it would be a positive 3 and angle pi over 3, and it'd still be the same exact point on the graph. So we have to be very careful because your points can be all sorts of different points, or they can be called all sorts of different things, but it's still the same point. They just have non-unique names. In the Cartesian or rectangular coordinate system, we're used to just one name for every point rather than infinitely many names. So now that we know that the names of our points aren't unique, here's a couple interesting facts. The point r theta and the point r theta plus 2n pi, so some multiple of 2 pi, represent the same point. And I'm using n to mean an integer, so a whole number. Also, r theta and negative r theta plus 2n plus 1 times pi represent the same point. And again, n is an integer. So if I'm keeping my r the same sign, I can come up with a new version of the point by adding an even multiple of pi. If I instead want my r to switch signs, so being negative instead of positive, I'm going to have my angle plus an odd multiple of pi, and I'll still get an equivalent point. So let's do an example finding different ways to write our points. So given 7, 3 pi over 2, find 2 other representations of this point. We're going to say one with r being positive and one with r being negative. And there are infinitely many correct answers to this. I'm just going to go with what my first instinct is for all of them. So when r is greater than 0, and I already have r greater than 0, I know my r is staying the same. So this is the first case we were talking about, where we can add an even multiple of pi to our angle. So I'm just going to add 2 pi to the angle, because that's just the first even multiple of pi I can think of. If I simplify this, I get 7 and 7 pi over 2 as another representation of the same point. A representation with a negative r, well, that would make this a negative 7. And I know from the definitions that I had just erased that I can get that by adding an odd multiple of pi to my angle. And the first odd multiple of pi I think of is pi. So I have negative 7 and 5 pi over 2 is another representation of this exact same point. And again, there are other representations out there. These are just the 2 I happen to choose to use. So now you might be wondering, with this polar coordinate system, how do I convert between polar coordinates and our standard XY rectangular coordinates and vice versa? And there are some formulas that we can use to change between these 2 different coordinate systems. So converting coordinate systems. To convert a point r theta from polar into rectangular xy, you need to use the formulas x equals r cosine of theta and y equals r sine of theta. And then to convert a point xy to its polar form r theta, use the relationships r squared equals x squared plus y squared, and tangent of theta equals y over x, as long as x is not 0. So now we're going to do an example where we convert between the different coordinate systems. The first example. Convert the polar point negative 10, negative 2 pi over 3 to rectangular coordinates. Well, I know from my definitions I just erased that x is equal to r cosine theta and y is going to be r sine theta. So let's start with x. X is r cosine of theta, and that means that my x is negative 10 times cosine of negative 2 pi over 3. Now, cosine of negative 2 pi over 3 is negative 1/2. So I get x is negative 10 times negative 1/2, which is positive 5. I'm going to do the same idea with my y. Y is r sine of theta. So y is negative 10 sine of negative 2 pi over 3, which means y is negative 10 times the negative square root of 3 over 2. So my y coordinate is positive 5 square root of 3. And that means converting it to rectangular coordinates, I get the point 5 square root of 3 as my answer for the XY rectangular coordinate version of that polar point. Let's do an example going the other way. So now let's convert the rectangular coordinate point, -2, -2 square root 3, to polar coordinates. With r greater than 0. Well, first I'm just going to find my r. We know from our formulas that r squared is equal to x squared plus y squared. So my r squared is equal to -2 squared plus -2 square root 3 squared. R squared is 4 plus 12. So r squared is 16, which means r would be either plus or minus 4, but since we're saying we want r to be greater than 0, we'll use r equals +4. And now I know that I want my theta to be defined by tangent of theta equals y over x, which means tangent of theta is -2 root 3 over -2, which is square root 3. But now's the tricky part. I know theta is going to be an inverse tangent of square root of 3, but let's take a look at what this point would look like. The point -2 root 3 is somewhere over here in quadrant 3. So I need to make sure that the angle that I choose ends up being in quadrant 3. So tangent inverse of square root of 3 in quadrant 3 is theta equals 4 pi over 3. Just calculating tangent inverse of root 3, you're going to get pi over 3, which is in quadrant 1, and you have to add pi to it to get over to quadrant 3. So now that I know my theta, I know that my polar coordinate version of this Cartesian point is 4 pi over 3. And that's just one of the many polar versions of that point. Let's do another example like that one. I'm sure you can tell converting from polar to Cartesian is much easier than converting from Cartesian to polar, just because there's only one way to write each point in the rectangular or Cartesian coordinates, but infinitely many ways to write them in polar coordinates. Let's do one more like that. Let's convert the point to -3 to polar coordinates with, again, a positive r. Well, let's find our r first. I know r squared is x squared plus y squared. So I get r squared is my 2 squared plus my -3 squared, so 4 plus 9. R squared is 13, so r is the square root of 13. Now for my theta, I know that tangent of theta should be equal to my y over x. So tangent of theta is equal to -3 over 2. Now, this one's a little tricky because it can be difficult to find this theta because we don't have a value on the unit circle that will give me that exact value for tangent. So let's first take a look at what this point would look like if I graphed it in rectangular coordinates. 2 and -3 is somewhere over here in quadrant 4. If I type into my calculator theta equals the tangent inverse of -3 over 2, I get that that's approximately -0.98. An angle of -0.98 would in fact be in quadrant 4, so we're good. And that means that my point is r, which is square root of 13, and theta, which the exact value for theta was tangent inverse of -3/2. Since the problem did not ask me to round to any particular decimal points, I'm using the exact answer, just writing tangent inverse -3/2 for my angle. So this is all about polar coordinates, but we can also have equations using polar coordinates rather than just using our x and y like we usually do. So a polar equation describes an equation with variables r and theta rather than x and y. So for an example, we are going to write an equivalent equation using polar coordinates. And my first one is going to be the equation y equals -3. So I'm going to convert the entire equation into a new equation. But we know from converting our points, y is equal to r sine theta. So this tells me r sine theta equals -3. If I solve that for r, I get r equals -3 over sine theta, which is the same thing as -3 cosecant of theta. And that is the polar equation that's equivalent to y equals -3. Another one. What about just y equals x squared? That's just our standard parabola. Well, let me plug in what I know about y and x. Y is r sine theta, and x is r cosine of theta. So when I square the right side, I get r sine theta equals r squared times cosine squared theta. I can divide both sides by an r. You get sine theta equals r times cosine squared theta. And then I can solve for r by dividing both sides by cosine squared. So I get sine of theta over cosine squared of theta is equal to r. But I can write this a little bit different too. I know sine over cosine is tangent. So I have tangent theta times another 1 over cosine of theta equals r. But 1 over cosine of theta is the same thing as secant of theta. So my polar equation is r equals tangent theta secant theta. And that's the same equation as y equals x squared, just converted to polar form. Let's do some more examples writing polar equations. No, actually, we're going to take polar equations and convert them to rectangular equations, just to show you that we can do this both directions. So let's write an equivalent equation using rectangular coordinates. So I'm going to rewrite my equation so that they have x's and y's. My first one, r equals -3. Well, one thing that I can do is think about all of the things we know. We know r squared is x squared plus y squared. Tangent theta is y over x. So I can change this into something I work with if I square both sides. that will get me an r squared. So if I square both sides, I get r squared equals 9. And then r squared is the same thing as x squared plus y squared. So I get x squared plus y squared equals 9, which we know this is the equation of a circle with radius 3, centered at the origin 0, 0. So a polar equation, r equals just the number, gives you a circle with that particular radius. That's kind of interesting. Let's do another example. Theta equals negative pi over 4. Well, I know I have an expression for tangent theta. Tangent theta is y over x. So let me rewrite this by taking the tangent of both sides. Tangent of theta equals tangent of negative pi over 4. So I would get y over x for my tangent theta, and the tangent of negative pi over 4 is negative 1. And then I can solve that for y to get a standard rectangular coordinate equation. I'll have y equals negative x, which is a line with slope negative 1. Through the origin, 0, 0. Let's do a couple more of these. What about the polar equation, r equals 6 secant of theta? Well, this time I have both r's and thetas in it. So I need to remember the relations that I know involving r's and thetas. That would be x equals r cosine theta and y equals r sine theta. Now, secant of theta, that's the same thing as 1 over cosine of theta. So I can write this as r equals 6 over cosine theta. Now I can multiply both sides by cosine theta, get r cosine theta equals 6, but r cosine theta is x. So I get x equals 6. And we have a vertical line from that particular graph. And just one more to finish up this example. Let's take the equation r equals 6 sine of theta, and we'll try to convert it into x's and y's. Now this one again uses both r's and thetas, so I'm going to want to somehow convert this to x's and y's. One thing I could do is, you would think we could maybe divide by sine theta, get all of that on one side, but I don't know what r over sine theta is. I only know what r times sine theta is. Well, on an earlier problem, we squared both sides, and that got me an r squared, which is x squared plus y squared. But I don't know how I would simplify 36 sine squared theta, so I would still be stuck. However, I can multiply both sides of the equation by r. So now I get r squared equals 6r sine theta, and this I can work with because r squared is x squared plus y squared, and r sine theta is y. And technically, this is already a Cartesian equation, and it is a correct answer. But what does this equation actually look like when we graph it? Well, I could move that 6y to the other side. And then I can complete the square on the y part. So I add 9 to both sides, and I can rewrite this as x squared plus y minus 3 in parentheses squared equals 9. And now it's very clear that this is a circle with radius 3 and center 0, 3. And so you can see that our polar equations often describe graphs that we're familiar with, but sometimes they don't. And you might be wondering, why do we even bother with this strange polar coordinate system? And the reason for that is because, quite frankly, some graphs are much easier to graph using polar coordinates rather than Cartesian coordinates or rectangular coordinates. In our next video, we're going to do a lot of graphing of polar equations. We also use polar coordinates a lot in calculus because sometimes it's easier to work with it in the other form rather than the standard rectangular form. So stay tuned for the next video to see how we graph a lot of these polar equations. There's a lot of really cool looking graphs we get with these. If you have any questions, feel free to drop them below. If you're a current student, you can also ask in email or office hours or in class. And I'll see you guys next time.